Dear colleagues, thank you all for attending this session, Superconductivity for a Sustainable Future, the Promise of HTS. I'd like to call to the stage João Martins, professor at Nova School of Science and Technology, who will run and moderate this session. Thanks a lot.
Feel free to sit. Okay, so welcome everyone. João, please. Not you, João Marcial. Okay, so hello everyone to this outreach event regarding superconductivity for a sustainable future, the promise of high-temperature superconductivity, and how can superconductivity help power the energy transition. Okay, by now you already understand that the only thing between you and the gala dinner is ourselves, so we try to be concise, quick, and give a very sharp vision of the needs of the HTS for the energy transition. This little talk is covering strategic vision, field experience, and industrial readiness. And we have the pleasure of having outstanding and distinguished panelists with us that I'm going to present by the order that they are going to speak. So we have Ziad Malham, which has a vast experience in superconductivity. He founded Oxford Quantum Solutions, an independent innovation consultancy. And recently, Ziad initiated the Superconductivity Global Alliance for cleaner, healthier, prospective, sustainable future developing. And it's a public-private partnership to address the future and the energy goals. Just one second, I will present everyone, and then I'll give you the word. Then we have Matthias Know, which is the director of the Institute for Technical Physics in Karlsruhe Institute of Technology. He collaborates with several universities, from Cambridge University, École Polytechnique de Montréal in Canada, and also with the Faculty of Electrical Engineering in Karlsruhe. We have Tabia Andert, I hope I did it right, the name, also from KIT, which she is the director of superconductive magnetic technology with a long career in the field. And I can highlight she received the IEEE Award for continuing significant contributions in the field of applied superconductivity. And Wolfgang Walter, which is the head of the magnet division, responsible for all superconductive and magnetic activities within the company Bilfinger, and is also a board member of Connectors, a professional association of European companies in vision of shared superconductivity commercialization around the world. And finally, last but not least, we have João Maciel, which is the managing director of EDP, Center for New Energy Technologies, which is our Portuguese DSO, dedicated to apply and research development in the energy sector. João has been serving in the EDP research and development for a long time, and he was the head of the Windflow project some years ago, and he's been with these new technologies for many years. So we'll start with 3 short presentations to set up the scene, and we start with the strategic vision. And the strategic vision, no, Ziad, the floor is yours. You can go, please. And Ziad will talk about superconductivity and the grand challenges in sustainability, and how superconducting technologies can support societal goals like decarbonization, grid stability, and sustainable growth.
Thank you, Joe, for the introduction and for the nice setup of this panel session. Thank you, Chairman, for the invitation. And we are short of time, so I will try to keep my complimentary notes to the minimum. Superconductivity and the grand challenges of sustainability. That's what Joe asked me to do. And he said an outreach, so I made one slide about where we started and where we are now. Superconductivity is a smart material which can offer capabilities not possible with other materials. It's discovered by accident, and there are over 6,000 superconducting materials being discovered so far. We're only using 6 of them. Superconductivity will make a big difference, especially HTS, in transmission. It's expected 5 to 10 in the first generation of transmission lines. It will make almost 50% reduction in the wind farms. It will provide over 80% reduction in size in some of these offshore capabilities. And you could see what ITER and CFS, more than 60% reduction in clean energy. So its impact is major and really will change a lot of our life, not just in power and energy applications, but on also other subjects. Over the years, just for we have seen various discoveries and technologies. It started by accident, and over 50 years before we saw the first commercial superconducting application. Commercially, it was started in 1961 by Oxford Instruments, St. Martin Wood. And within 10 years from discovery, the first commercial MRI. And MRI, superconducting MRI, made a step change in our life, in health and life quality. No one is now not being affected by the impact of diagnostics using superconducting MRI at a large scale. And then we start to see the new frontiers: physical sciences, life sciences, energy application. And in the 80s, we discover the discovery of HTS materials, which is now we start to see the early stage of deploying it in so many applications. Nowadays, we are seeing a new endeavor to go into new applications, into quantum, energy, healthcare, fusion, transport, and large scale. But what are the drivers for superconducting application? And there are 4 drivers. The green economy is one of the major drivers for future superconductivity. UN Sustainable Development Goals. It's about sustainability we are talking today. And the United Nations in 2015 identified 17 Sustainable Development Goals. We have the low temperature superconductor. It's not only HTS will make a difference, superconductivity will make a difference. We have seen the last 10 years what cryogen-free solutions has made to MRI. 20 years ago, 30 years ago, we were using about over 1,000 liters of helium. Nowadays, an MRI system, less than 1 liter, would be running for a year with a closed cycle. So it's not very sustainable solutions. And of course, we start to see the HTS taking us away from the 4K to 20K to start with, but I can see it taking us to 40K and 70K. And all these will lead to a greener, healthier, and more prosperous and sustainable future. I thought I would share you one example about MRI. So people are take it as a black box, but really it has made a major step change in deployment. Now it is a commodity. You order an MRI, you get it within 3 months. 20, 30 years ago, you have to wait over 18 months. MRI has gone through this stage of slow, what we are doing now in application, very slow, painful, expensive introduction. But it has developed an ecosystem. The supply chain has high quality control, regulated, and in a timely manner. More important as well, we have to start to see the supply of MRI moved away from 50 to 100 a year to over 5,000 MRI systems a year, and it's a commodity now, you just buy it. And what we have seen as well, what MRI enabled in new solutions in cryogen-free systems. Now, we could see the emergence of all the new MRIs relying on low helium supply. This is something which I saw in 2021 and opened our eyes about the opportunities superconducting can offer for us. It is showing a Bloomberg real data about the global electricity generation mix. It's showing that by the data from 1970 till 2020 is real data. This is something Bloomberg accumulated and made a forecast based on the solar, wind, and so on. The first message saying that by 2050, which was the original target for getting 1.5 degree carbon emission capturing, basically saying that whatever we do in solar and wind farm, it will not get us to the 1.5 target by 2050. We will left with 30% of still carbon emission. And the other message saying that this 30% is the driver for all these fusion companies. We have over 45 private companies in fusion. They are targeting the $6 trillion market, which will be available for us in 2050. And the other message from this one, that the wind farm, you could see a small portion. The full wind farm market, we don't have enough material to deliver on the wind farm. Superconductivity will be essential to enable the future wind farms. Connecting all these solar farms will require superconducting substations. So you could see that superconductivity will be instrumental in making our future more sustainable. Opportunities, I just want to say that these massive numbers coming out from various market research, but they are enormous. The wind power is 1.5 trillion, compact fusion 40 trillion, MRI 40 billion, cancer treatment 20 billion, science discovery 8 billion. All these are really will be drivers for sustainable society. So that's where we come to the Superconducting Global Alliance, and it's addressing how we can take these opportunities and these challenges going forward. What we are proposing is a community working together with the investors and the big industrials to provide the greener, healthier, and more prosperous, sustainable future. That will lead to 4 smart markets. The smart market in computing and electronics, the smart market in energy, power, and transport, science discovery, and of course, healthcare. These combined with the 17 Sustainable Development Goals will require 5 targets. The first one is developing public and private partnership. Public will not deliver on this potential, private will not deliver on this potential. The partnership between public and private is critical to deliver on the promise from superconductivity. We need to develop consortia and partnerships to deliver on these opportunities. We need to have a global summit like the COP meetings where we, the whole national and industrial partners commit to targets for introducing these solutions. We need national strategy and, of course, national initiatives like Quantum Initiative, which 1 billion plus, to enable accelerating of introduction of these solutions. And really, the ambition is how we can take the superconductivity from the frontier end to the mainstream, how we can make superconductivity like a semiconductor industry. Not talking about millions or billions, but trillions. It's how we can have the vision for making superconductivity economically viable. We need to foster cross-industry adoption by 2035 and build a resilient global value chain. This will require an investment strategy. National initiatives will be at the heart of it, where government will encourage accelerating the private sector, the industry, to accelerate introducing of these solutions. And basically, return on investments forecast by application domain. We have, over the last 30 years, we have over 200 senior experts, part of this global alliance in the USA and in Southeast Asia, in Europe and the UK. Industry, research institution, and university. And they come out with over 30 grand challenges. We have already completed 3 white papers on fusion in energy and power, on transport, healthcare, superconducting electronics and quantum information processing, and science discovery. These 30 grand challenges are the first shot. I'm sure there will be more grand challenges coming forward. And these will require really funding, serious funding. And so we came out with a strategic roadmap in 2025 to 30, focus on R&D, pilots, and early commercial adopters for these grand challenges, commercial deployment for the beginnings, and infrastructure scaling. So if you have the money now to deliver 100 miles of transmission line, you don't have the materials, you don't have the workforce, you don't have the skills. That's what we have to think about, how we develop the ecosystem to address the potential from these benefits. And by 2035, 2045, we hope the mass adoption and the global integration. The impact on sustainability is enormous. I mean, I mentioned 17, so I looked closely at each one of them. For example, on the good health, it's really about medical diagnostic and imaging, quality education, demonstration. If any of you have started working on computing, it was a punch card. Now you have all the computing in your laptop. You go to a university, you find large room of computers working on these things, and so on. So these all nine sustainable development goals are making an impact. I just want to say these technologies are in energy efficiency, grid resilience, sustainable transportation, quantum digital infrastructure, and healthcare. And I want to summarize by superconductivity ecosystem to deliver on the promise of greener, healthier, and more sustainable future. Superconductivity needs private and public partnerships and national and global initiatives to deliver on the promise. And thank you.
Thank you. Thank you very much, Said, for the very nice strategic vision approach. We'll now hear from Matthias and Tabea from the KIT about field experience and lessons learned from the field. What has been learned regarding real-world energy systems, namely fault current limiters and power cables. Please, thank you.
Yeah, good evening, ladies and gentlemen, and thank you very much for this kind invitation. We would like to contribute, Professor Arndt and myself, to answer to the question what has been learned from the field test of HTS power application in the past, especially cables, fault current limiters, that's my part, and rotating machines and magnetic billet heaters for Professor Arndt. Yeah. I'm in this field now for 34 years, and I have heard a lot of comments in the past about power system application, especially when it comes to cables. Yeah. A superconducting cable is, of course, expensive and not reliable, or this makes no sense. Yeah. And why the hell should we use it? Yeah? Or it's expensive and is no solution for a transmission grid. Yeah. And in recent years, if there is a need, we don't care about money because we have to do the energy transition anyway. Yeah. And maybe some of these comments were triggered by the first lessons learned from the field tests. Yeah. In the very beginning, 2000, 2001, the Detroit and the Copenhagen cable were quite a challenge because the results were not very encouraging. The Detroit cable could not be energized, the failure in the cryogenic system, and Copenhagen was already very difficult to run for a long time with the reliability of that time cooling system. Yeah. But latest since Doug Willen presentation yesterday, you are here as a co-author of the successful field test of pre-qualification of 110 kilovolt, or the Weir cable company doing this as a product, yeah, or the successful Chinese and Korean and Japanese applications. We know that times have changed, and one of the first cables that ran for a very long time was operated 1st of April in 2014, and it ran for 7 years. And if you see at the lessons learned, you would say these are minor revisions only. Yeah? Unbalanced capacitance, a little bit of leakage in the cooling, and the automatic reclosing system, because we were careful at the beginning. And this was a first of a kind installation. Nexans did not make this before. Yeah. And if you look today, I would say up to medium voltage and high voltage cable, the technical issues are solved. That's why we see companies here around that have business plans to sell it maybe to data centers or some other applications. Yeah. And the reason changed why you want to use it, because copper is getting more expensive, space is more valuable than before. Yeah. So far about the cables with the current limiters. I had the privilege to participate in the first field test ever of a resistive type current limiter, also energized in April 2004 for 1 year. At that time it was bulk material available, and also these lessons learned were quite successful. If you look at the results, you can fulfill all technical requirements. Yeah, that was the important thing. The data recording, even without the mobile phones and this broadcasting system, was very easy, but it worked. As always, you have to adapt something, minor adaptation of the cryogenic system. And during that year, no 3-phase, but a 1-phase short circuit occurred. Yeah. And you know, since today, you have seen now fault current limiters up to 220 kilovolts working reliable for several years in the grid. We have some of them also in China in operation since a few years. And also these lessons learned, that's always the same. If you start as a new company, you need some minor adaptations with the cryogenics. Yeah, I would not say that it didn't work. Yeah. And in this specific application in Moscow, you have a few challenges because it's a transformer feeder. Transformer means a long recovery time and recovery under load. But there are many applications where you have a coupler location, where you have a short fault duration and where you need no recovery under load. And that's why we see many activities going on. We have also seen a few in this company. And one final comment before Professor Arndt takes over. When we have a look at the share of the cost of the superconductor, this is no longer dominating. Yeah. In cable and fault current limiter applications, the share of the cost of the superconducting material is not the biggest part any longer, and this makes us quite confident that we see more of this in the future.
Thank you, Professor Nuhr, for this introduction into the topic. And I would like to move forward to moving things, applications of superconductivity, and this is rotating machines. I have to apologize that I picked only some machines in here, but for some purpose, just for the learning effect. So what you see, for example, in the top left corner there is what I would call a old lady. This was the very first HTS machine built before 2000, and finally it was reactivated about 15 years after first inauguration in Australia, and it showed the same performance. So this is what we can learn from this. If an HTS machine is working right from the beginning, it will do that job even after 15 years and more. So what I put together is citations from people involved in this project. So what came out of that is superconducting machines, rotating machines provide viable concepts. They offer an improved power density in there, a higher efficiency, and there was a statement, a future with a new generation of very compact and efficient large electric machines. And this led to the fact that one of these blue machines was operated for more than 5 years in an industrial environment, and this was really stated after that. The performance as expected, low cryogenic cooling input, very lightweight, and an efficiency increase in there. So this is really promising, but however, we have not a lot of HTS machines in the field, despite the fact that all these machines performed as expected. However, there have been some groundbreaking projects in Europe. This, for example, was the installation of a wind power generator, an HTS wind power generator. And what is really important there is that this project managed to increase the technology readiness levels of the critical technologies the technology bricks for that to a level higher than 6. So this means it's very near or elaborated to a market introduction in principle. What still lacks is this sweet spot for the business case. And what you see is the benefits. It's very compact, these type of machines. They are a little bit more lightweight. The power rating is definitely increased, what we learned already from the past slide, and it's an overall cost reduction for that. So we see there is a technical success without the sweet spot in business so far. And this led to the international effort in creating a roadmap for these superconducting rotating machines. And it was stated that in principle all these kinds of applications have been stated already and demonstrated. And again, the key technology issues are resolved. At that time, when this review, this roadmap was created in 2017, there was still the cost of superconductors and the cooling system a major hurdle. But this is not the case anymore, thanks to the fusion activities, for example. And robust mechanical properties are really required in there, but I think nowadays we can solve on that. And then I come to a, let's say, hidden champion, a silent champion. This is the magnetic billet heater, and two of these types of machines are operated, at least in Germany, since more than 15 years in the field without any complaints. So this is really a sweet spot for this application, and tomorrow there will be talks on that. And what is really important there is that you can increase the heating efficiency to novel unrivaled levels in there. And there was a statement from the company selling these type of machines that high temperature superconductors are the key technology for the 21st century. And with that, I come already to the conclusions from this field, and I think this holds for the things Professor Noah said, and as well as for the statements I have had here. The technical and operational requirements are all fulfilled. This is not a challenge anymore. We had already several long-term field operations of rotating machines, as well as with magnetic billet heater, for example. What we have to state is that the cost share of HTS material is not the biggest one in the applications anymore. This is really decreasing. And the good news is that more and more permanent HTS energy applications are in realization. However, system improvements are always appreciated. We have still some development in system integration and standardization, and this might help the newcomers in the market to pick up this technology. And with this, I thank you for your attention and hand over to the next speaker.
Thank you. Thank you, Tabi and Matthias, for a nice presentation regarding field experience. Now we have Wolfgang Walter, and he will address the industrial deployment, basically barriers and business opportunities, and how can we bring HTS to the market. Thank you.
Thank you for the introduction, and good evening, everybody. So I want to talk about bringing HTS products to market, barriers, opportunities, a very broad topic. So I will focus only on a market of sustainable energy products. I will give this, or I'm giving this talk on behalf of Connectus, European Industry Association of companies who support superconductivity. Members of Connectus range from producers of material and conductor to system producers and to suppliers of auxiliary systems. My personal background on this field comes from my work at Bilfinger, where I was involved in the development of a first superconducting solenoid system for a spin echo spectrometer that increased or improved the resolution of such spectrometers. We developed superconducting undulators and brought them to the market as product. We've also developed a flywheel with a superconducting bearing and a magnetic trap for transporting antimatter on the road. Unfortunately, there's not too many people who want to transport antimatter on the road, so this is a case of not a real product, but a project. This brings you back to the topic, the products in HTS. I will touch on market opportunities, what it means to bring a product to market, talk on typical barriers, about technology readiness, and I will highlight this with two cases, one from energy storage and one from sustainable energy generation. So we want to have a sustainable product. There's basically three strategies on how we can be more sustainable. We can be more efficient, meaning basically getting more out of less or the same. We can be more consistent, for example, if we use renewable sources or recycling, or we can be more sufficient, meaning consuming less. The first two strategies lead to a variety of product candidates. The third is something we can all work on ourselves. On the right side, you see some known candidates for products. There's the power generation, where we could use superconductivity within fusion or for superconducting generators. For transmission and distribution, there is the cables and associated products such as fault current limiters. And there is energy storage with flywheels, SMES. We could couple liquid hydrogen technology with HTS. We could work on magnetic separation for recycling using HTS magnets and so on. So there is lots of possibilities. Looking at this from point of view of a company, the company can work on developing a marketable product, which is a technology-driven process, and they can and have to work on the introduction of the product to market with sales. All these need considerable effort. And with effort, I don't mean only the invest in terms of money, but also the invest in terms of key resources. And there are some boundary conditions that we really have to take into account here, otherwise there's huge risks for such a project. Is there a market for the product? Not now, but at the time of the market introduction. Can a product be successfully developed in time, cost, quality? Will the product be competitive on the market? What are the USPs? What is the target price? So in general, market introduction is the highest risk phase in a product life cycle, and we really have to have a clear vision for a product to start such a process. Now coming to typical market barriers for HTS products, I picked out two. One I would call late benefit. HTS products are often high-tech products. This means the development effort is rather high and the time to market rather low. Often in industry, when we talk about developments, we are talking about time scales of weeks or months. For typical HTS products, we are rather on the order of years. From the point of view of the consumer, there is also a late benefit, because for a sustainable product, the benefit often does not come in form of CapEx, but only in form of the OpEx when we use it. However, there is an exception if superconductivity is actually the technology that's enabling us to develop and produce a product. Good example for that was already mentioned by Siad, the case of MRI in the past. Second barrier, the conservative energy market. We really have to take this into account, and at the beginning of Matthias Noah's talk, there was all these citations showing really that people are conservative in this market, and we have to be very careful that we have reliable and easy to use products. But there I think we have improved quite a bit, especially in the field of cryogenics in the last decade. And still we should not forget HTS can solve existing problems in unique ways. The superconducting fault current limiter was already mentioned, and for the sustainable energy production, there is, for example, fusion. Coming to the technology readiness level, we have already seen in the previous presentation by KIT, the technology readiness level for the products in HTS is rather high. This is not the issue. Rather, if you want to develop a product in this field, we should be careful on what kind of IP is protected there and should have a strategy for that. Now I come to the first case, the case of an energy storage. There's two well-known energy storage systems using HTS, one being the SMES, the superconducting magnetic energy storage, and the second being a flywheel with a superconducting bearing. That's the one I will focus on here. With a superconducting bearing, you can have your rotating mass levitating without touching it, and the whole system is self-centering, so you only need a passive control. There's no need for an active control. Such systems can provide really a high power in a small footprint. This is illustrated on the graph on the left side, where we see the specific power over the specific energy for different types of storages. What does this mean now from the market point of view? Well, actually, there is a limitation. The flywheel storage is not a mass energy storage system, so we can only address a part of this energy storage market, only a niche actually. But nevertheless, a niche market can be very interesting. So what about barriers and competing technologies? Barriers, I would see first, the energy market, as I already mentioned, is a conservative market with established solutions. So we really have to have good arguments for the people there. And also the energy market, when it comes to, for example, power quality, is highly regulated. So we have to take into account the political regulation situation. Competition for a flywheel, there is two types of competition. The high-tech competition from supercaps and SMES, but more critical, I would rate here the competition from just classical batteries. Prices of batteries dropped significantly over the last decade, and this is really a tough competition if you want to bring a flywheel on the market. Second example, sustainable energy production. We see a growing energy consumption, and this situation becomes even more severe now due to the situation that we have with AI. Fusion can provide a unique solution to this pressing problem. It is sustainable, it is efficient, reliable, and potentially, and it is also safe. So there's a high potential for this. And I think now is also the right time to work on that, because on the one side we have scientific successes of the last years, where Wendelstein 7X showed that we can handle plasma on a long time scale stable. At the National Ignition Facility, the ignition of a plasma was proven, and HTS technology advanced significantly, which allows us to make such power plants much more compact and efficient. There is also support now from public and private side, and so it's no wonder that at the moment more than 50 companies worldwide develop fusion power plants with complementary approaches. So let's also look here at market and barriers and so on. The accessible market, it's huge. Bloomberg in 2021 made an analysis stating nuclear fusion market could achieve $40 trillion. Competing technologies are there. We have existing power plant technologies that are competition and that are also developing. For example, on the fission sector, we have the SMR, sorry, there's a typo, it should be SMRs, the small modular reactors that are heavily developed at the moment. And also on the fusion side, there's actually a competition. One could also think about building a fusion power plant with lasers without HTS. So challenges are there. There's the challenge to develop the HTS coils, but I don't think that this is really the most severe challenge. The really challenge where we need also still research has to do with materials, with first wall, with the tritium preheating circuit. However, I am convinced that we can and will make fusion power plants work. Remains the question, will they be competitive? I think it's too early to answer that question, and we should work on that to come to a point where we can answer it. Summarizing, products with HTS need clear USPs. This actually holds for most products. HTS are high-tech products with a high development effort. They benefit often only due to the OPEX. TRL is not the issue here. And due to sustainability requirements, there's new chances on the market. HTS products are more efficient or can even enable new solutions. So let's seize the opportunity and let's work on HTS for sustainability. Thank you.
Thank you, Wolfgang. Okay, so let's here start the discussion. And I would like to start with João Maciel, because he's the prospective HTS user point of view. And João, what, for your reasoning, are the main drivers for adopting superconducting technologies in the grid? And also, what are the specific use cases where you're seeing HTS are attractive for utilities, and what kind of performance or reliability you expect as a user from the technologies?
Okay, thank you. Pleasure to be here. Thanks for the invitation. Well, big question, several questions in one, and let me just go one step back even, which is to let you know that I'm part of VDP, which is a energy company. We have a strong presence now in around 30 countries, a lot of focus in renewables. Just to give you a figure, last year, 95% of the energy we produced worldwide was renewable. And so we are very committed with the energy transition. This was a path that took already more than 20 years, and we are taking this path. Well, the energy transition is a huge challenge, as we all realize. So I think we need to change in 30 years what took us like 200 years to consolidate. So we need to do things differently, and this means producing cleaner energy on the renewable side. Also acting on the demand side, so because we need to electrify industry and a number of things on the demand side, so that we also can remove emissions from the demand side. And there's also like a third avenue, which I would call them enablers, but which are grids and storage, for example. I mean, as the World Energy Agency was pointing out, I mean, grids must not be the, let's say, the bottleneck for this energy transition. And I guess this may be, to some extent, an inflection point here, even for HTS. The fact that grids may be becoming a bottleneck for the energy transition. So we need to do things differently on the grid side. There are many energy transition has a lot to do with let's say, there are many technologies that will enable the energy transition, but there are also other things which are relevant. One is, of course, we need to do things much faster and at scale, be it in renewables, be it in grids. So we need to do things differently. If we think, for example, last year, 2024, we already had like 2 trillion investment in energy transition, but we need to multiply this by 3. And so we need to be at around 5 trillion investment per year between now and 2050, because we'll need to multiply by 3 the renewables capacity, double the size of our grid, and so this brings me to the grid. So On the grid side, there are several things that we can do. One thing is let's say, to look at what we have and take the most from the existing capacity. And this means explore it to the fullest with sensors, with the dynamic load rating, a number of things that could take the most of the capacity that we have. A second step would be, I would say, also more or less not changing technology, deploy it differently. For example, using automation to deploy it much faster, or for example, let's consider, for example, overhead lines, addressing topics like the way we build lines, the way we build foundations, the way we deploy the grids using drones, etc. So there's a lot of things to do still on, let's say, with the regular technology. But then, I guess this only brings us to a certain point. So we do need other technologies. HTS, I believe, is a big promise, which is the headline for this session. There are other, I would call them competitors, like DC, for example, distributed current. And I do think that to some extent that DC faces similar challenges to HTS, in the sense that it is a paradigm shift. It may make sense if you are producing on DC and your demand is on DC, that your system could be DC, but I mean, you have a full legacy AC system. And so this brings us, I guess, to the same kind of discussion on what confidence we need to build in order to change. So this brings us to your question. Sorry. To your question, I mean, I guess it's quite obvious. I mean, the drivers for HTS are the ones that have to do with the capacity that this technology brings, which is being able to have more capacity for the same land use, having less losses. So I mean, this and for those things, use cases that have to do with the very dense urban areas where it is almost impossible to build a new line, or even if you think retrofitting existing lines to increase capacity, and aging infrastructure and all this. This is, of course, an opportunity for this HS technology to come. I mean, lines is of course one. So cable technology, but as well transformers and all the other ancillary topics, fault current limiters and all this, are also relevant. But I mean, of course, I mean, I don't want to answer all questions in the first one, but I mean, we must be on the money, right, to be able to do it. And we do think that being on the money means total cost of ownership, not only capex or opex or a simple sum of both. We could call something like levelized cost of superconducting. We use this term levelized cost of energy, but I mean, we need to take into consideration everything in order to make this calculation. And as well, the fact that being a new technology, so more risky, even regardless of all the demonstration that already took place, it's still regarded as more risky to some extent because there's less experience. When you look at an investment, for example, there's something called the weighted average cost of capital, which is how much your money costs, your equity and your debt. And so if you are looking at riskier technologies, from the start you are starting your race back, because your weighted average cost of capital for a riskier technology is higher. So you need to ask more return to your investment to be able to do a right business case. But I'll leave it here.
Thank you. But what you say leads me to something that I want to ask Ziad, because you mentioned the need to be faster and to have more investment, also regardless the reliability. And Ziad mentioned in his presentation several applications, consortiums of private-public partnerships, strategic roadmap, public funding. But in your view, what is needed to accelerate the adoption? I mean, what technologies should be integrated? What use cases should be considered to have a faster deployment and at the same time keep the safeguard of the grid? So where can we act rapidly?
Yeah, we need to connect really with the need of our society. We shouldn't offer them components. We should offer them solutions. That's where we should start. We can do all these components. We have confidence, but our message should be that a technology can deliver on the need of the society. So, for example, in the power grid, they are not interested in the AC losses or the quench or the performance. They want to connect A and B reliably and continuously. So we need to start and talk their language. Utilities are very conservative, and they are not looking for problems. They are looking for solutions. So this is the first thing we need as a community, to bring awareness that this technology can address the need for our society. And we need to talk their language. Their language is, can you solve this problem for me? Why I should use HTS if I'm happy with what I have? So that's what we have to adapt ourselves and develop the solutions. So I can make a fault current limiter and so on. I can make a transmission line. But these utilities are not interested in this. They are interested how it will integrate in their utilities, in their system. And I think that's where we should start. Offering solutions and understanding the system integration of these solutions, for example, in the utilities or the energy supply. Now, the second question is, does it add value to our society? There's carbon emission, which we have to do that. There's a supply limitation. If some of you are following on the copper supply, basically, even if we have new mines, the price will continue to go up. So you need to come with a new solution. A superconductivity offer significant efficiency, not just in performance, but also in footprint. So, and in that footprint, you get simplicity of integration. So you could see that the journey from ITER to Commonwealth Fusion Combat Device, the system integration became simpler with HTS. So there's advantages for us to deploy these high performance, high quality, and the challenge for engineering it is basically we should be linked to the end solution, not to the demonstration.
Okay, I'll get back to you in the solutions, but let me hear what Matthias and Tabia, because you mentioned, and you also mentioned the solutions and the systems, and you highlight a lot in your presentation the longevity and reliability of the solutions that you present. So let's look, let's say, 10, 15 years ahead, where I'm already retired, so I don't care, but let's look at the time. And in your, let's say, view, what are the performance or reliability metrics that we can use to convince power grid operators that these tools and services are actually something that they can use? And also, I would like you to address the knowledge gaps that you think that require further investigation. Let's look a little bit here at the investigation to standardize and make these systems ready for commercialization.
Oh yeah, you mentioned the reliability first, what we can expect in 10 years. As I have tried to figure out here, that we already can achieve the reliability if we work together. Yeah? All the system integrator, the cryogenic people, the technology development, the industry. I'm sure ABB has not a big background in cryogenics so far. Yeah?
No.
But you have to learn it and you have to adapt it because the customer wants one hand only. Yeah? One system integrator, system provider only. Yeah? And the more and more demonstrations we see, the more reliability and credit we have for this. And I'm sure we will see this because otherwise we wouldn't have seen the big private investment in these companies. Yeah? Look at this, what happened in the past when you acquire 100 millions and more to develop cables. Yeah? Or we privately participate in a company and spend money to develop industry busbars with superconductors. Yeah? And I'm sure we will see that we have reliable applications. Yeah? And the second question, what is the gap?
The knowledge gaps that you think that still are there
the knowledge
in terms
gap,
of research.
The knowledge gap in the projects we have is among the different participants. Yeah? If you talk to each other in a different language as a cryogenic engineer, to me as an electrical engineer, and maybe to a salesperson that has to bring this to the market. Yeah? And when you this is what you have to bring together, and then I think we have several examples that this will work very successfully. Yeah. And you see the audience we have here, the bigger attendance we have each conference here, we are on the right way. Of course, nothing is solved. Yeah? Not the big market is not yet entered, but it always starts that way. Yeah? That you have a big promise, and then you follow the small curve that then starts very fast. And I think we are exactly at that moment before we see a fast integration of superconductivity in the grid.
Okay. Tillia, may just one comment, and also if you may, give also your opinion about standardization and grid code. So because if we talk about the grid, they are very, very keen about standards and grid code. So
for standardization purposes, it's a little bit too early to discuss that. But Matthias worked in a group for standardization of cables and fault current limiters for a long time. So there are already existing rules for that. But I wanted to pick up this risk awareness of the uptakers, so to speak. And I think it's really important not only to think in terms of reliability, but in terms of de-risking. And this is exactly what you said. You need experienced teams which rely on each other. For example, some 10 years ago, I was asked with my team to install a superconducting fault current limiter at a utility grid. And they said, no, we do not want to have a startup producing our superconducting fault current limiter. We would like to have a company which is behind that, with all the knowledge in one hand, what Matthias said. And this means if we are really putting new technologies into the market, then we have to assure that there is long-term support in knowledge and maintenance too. And this means all the partners have to be aware in that. So de-risking the technology introduction is key.
I think you're right, because it's not only working alone, but working together.
Yeah.
And in these emergent areas, working together sometimes is the most important thing. And this leaves me a question to Wolfgang that is connected with this. You mentioned time to market, which is, I think, is crucial in these new technologies. Also, you mentioned very important, and João will forgive me, the power grid operators are very conservative. So if you want to bring something new to them, you have to be very, very, very convincing. However, you also show us very high TRL. So how can we manage this balance? On one side, we already have high TRL, but on side, we have a very conservative industry. So how can we, from the point of view of sustainability, use these two aspects actually to enter into the energy market?
Yes, I think the answer is a bit twofold. The one is on the time to market topic and how can we bring systems faster to the market. I think we can learn from the attitude that the fusion startups show us, that take certain risks in their development process and just make things, risking a failure in the development, and if they fail, then they go the other route, and they don't try to explore on a theoretical level each and every possible route before realizing something. I think there also industry and research together are sometimes a bit too old-fashioned and conservative, and there is a potential to speed up. When it comes to the conservative market, I think there's two things. First, clearly we have to, on the one side, show them that we have validated solutions, meaning also solutions that are tested on a longer time scale. Sometimes this is a problem within the funding scheme, that we don't have a funding for a long-term testing. And the other thing is we have to address to them and make clear what problem we solve where we have an additional solution that they might want to have. I think in many cases it's not enough to be just a bit better than existing solutions. We have to solve really problems that they have, and I think then we can also get in touch with conservative markets.
Yeah. Yes, thank you, because I know João wants to speak, but I would give the word to you, don't worry. Taking these, what are, in a, let's say, short sentence, biggest barriers that utilities consider to be an issue, and what do you think the academia and industry can do, in this case, together to overcome these barriers and to, forgive me for what I'm saying, but to convince DSOs to actually adopt?
Yeah. Yeah, just wanted to make one brief comment on what was said. First, to fully agree with Professor Matthias on the topic that we are, let's say, generation and electricity distribution company, and so when we talk cryogenics, we must learn this and we must have hands-on knowledge. And so pilots, etc., of course, have a role also in educating the teams and the company that on new technologies. I mean, for example, I'll give you another example in Green H2, which is a completely different topic. But I mean, we are running pilots because we are an electricity company, and I mean, we don't understand molecules and valves, and so we need to get hands-on knowledge. On the topic of TRL, I mean, I think either the other or you touched upon this, which is I think there is high TRL in some components, but I mean, I challenge if there's a high TRL on system level. Or even market readiness level, which is also another scale, but also with has to do with packaging that we do and addressing concrete use cases, and so I guess this is relevant. But to your question, João, I mean, of course, one of the biggest barriers, at least perceived barriers, is cost, and with this holistic view on cost, there is still a perception that cost is higher. So. And of course, cost is not relevant if you want to run a pilot, but cost is relevant if you want to scale it to massively. And so there's this perception that just because the way it looks with the, or sometimes this image from the past may be frozen with the huge infrastructure, this may be lighter now and different, but still the perception exists. Of course, it has to do, of course, with complexity, and so electricity systems are sometimes not, or grids are not very efficient, but they are very reliable. They are efficient as well, but I mean, they are very reliable, so they exist for a long time, and so to change, that's why people are conservative, because the system works. A transformer works for like 50 years, and these things work. And so of course, this cost of change and introducing additional complexity on the system. I guess we also need long-term reliability data, meaning what is the maintenance cycle, concrete maintenance cycles that this will do, how much will this cost us every year on OPEX, namely on the cooling part, which is the most unknown part to us. And then other topics like integrating this with our SCADA systems. I mean, but this I'll say it's perhaps a second-order issue. But on the last question, which is our asks for, let's say, for academia, or for tech, or for regulation, I would say that one is perhaps we should be closer in co-developing the solutions now. I mean, the use case and technologies should be developed hand in hand from the start, and perhaps this is still a bit. There's still a bit of a disconnect between what is the development arena and what is the application arena. Things like modularization, thinking modularization from the start, so that its application is wider. I think it's also relevant. On the regulatory side, I mean, this is a heavily regulated area, and so, I mean, we have you were asking about standardization. I think you had in mind grid codes and all this, like quality, voltage, quality of the voltage wave, etc. And so we must comply with this, and so we cannot fail. We cannot risk our quality indicators go down. Otherwise, we lose clients, we lose concessions. So, but that said, this is the chicken and the egg. I mean, technology needs room to be developed. So we always end up in this, which is some sort of sandboxing, some private area where we could test stuff. And I do think that the regulators are more and more inclined to do this in the sense that they understand what I said in the beginning, which is if we do things the same way we've been doing for the last 200 years, we will end up where we are.
Thank you. And in this last short round of questions, and Ziad, I would like to have also your view regarding how companies in research can get together to increase the TRL as a system, not only as a component, but as a system, and at the same time reducing costs. Because what we've seen in the past, for example, with the PV, is actually the main driver was when the cost goes down. Before that, no PV penetration. So what do you
that's
think
exactly
as
the
a
right
strategic
question.
view?
From what we have seen in terms of challenges going forward, a company will not take introduction of new technologies on their own. And the public will not introduce a technology. So the space program, which has happened about 40, 50 years ago with public funding, if it's now, it will not happen. And you could see now private companies are sending assets to space. So the public funding will not take any of these challenges. If you look at the European space program, done completely funding from the national government, it will not happen again. So there's a change in public funding. And private funding, they have priorities. They have report to shareholders, and they can't just go into introducing new technologies which will take more than 3 to 5 years to introduce. That's too expensive. That's not rare. And that's where we are advocating for a public and private partnerships. The public funding will be responsible for retiring the risk, which allow companies, so instead of putting 10 million to develop a solution, they can put 5 million, and that will become easier for them to introduce. So public and private partnership is critical for introducing these companies. Now, the second question is the research community with the expertise on developing these technologies should be working with companies on end user rather than demonstrating technology, not offline testing. Say, for example, we would like to introduce 5 miles of transmission line with the system integration into a station, like what's happening now, retrofitting in Munich or in Paris of these transmission line. The need is forcing these authorities to introduce these solutions. So that's where you can get the partnership between the research, where the expertise now, and where the frontiers end in our vision, moving into the mainstream, or where it fits into the utilities. And so this partnership in understanding the needs of the end user, the customer, and building a program which is costed that the public funding accelerating, retiring the risks. So we have a good example of the Commonwealth Fusion with serious funding. They managed to demonstrate large device which none of the previous funding managed to do that. So serious funding will make a difference. I would just want to comment on 2 issues, or 2 points we mentioned, reliability and cost. So if you look at superconducting magnets, I've been in this field commercially for over 35 years. There are systems still running over 40 years old. So this technology is reliable as a component. So it will, now, if you look at the cost of an MRI system now, which is a full ecosystem, is that you can buy it now with fixed prices and so on, is less than 15% what it was about 25 years ago. So the scale economy will address the cost. I'm confident of that. And you could see the time of, it took almost about 12 years for MRI systems go from 5, 10 a year to 200 It took about, and that's where we are now. We are in the first, if you look at the cycle of 10, 15 years, we are at the early stage of getting these HTS components. So it will happen. The scale economy will take care of that. My suspicion, we can speed that up by public funding and private partnership. This 10, 12 can become even 5, 7 if this partnership. So we believe this serious investment, and that's why we believe a superconductive initiative at national level is required. So the current funding scheme is very good for learning and skills. That's how I see it. We are improving our learning, we are improving our skills. But if you want to introduce this to like an end user utility, it's not enough. And we need to encourage the end users to really to work with this technology by reducing the risk, either in cost or in technology. Hence, I think that's where we can get that partnership to accelerate the introduction.
Thank you, Ziad. And following that, Matthias and Tabia, do you think that this private or public funding should be applied already for reducing costs? I mean, are we in a stage where the research already made the proof of concept, and more than the proof of concept, because we already have a lot of systems deployed, but should we need to increase the research in order to reduce the cost of the solution? Is still yet? No? What do you think?
Okay. I think the reduction of cost will come by volume by itself. So this is natural. This was the same with the MRI systems. This was the magnet cost for nowadays is negligible to the initial cost. So this is so in principle, I think cost is not the main driver or the initial driver for that. What should be the initial driver is exactly what you said as public-private partnership, but I would say it's sufficient to have new consortia on system level with industry, the uptaker, the end user in the driver's seat. This is important. And then this knowledge build up and increase of TRL on system level will come by itself.
Maybe I can add, as a researcher, of course, research is important and we have to increase it. But in the past, we had several promises. The promise of electromobility, sustainable mobility. Yeah. The promise of renewable energy with photovoltaics. And now we follow the promise of sustainable, unlimited energy with fusion. Yeah. And when I look at this, what we see before, cost reduction comes usually with scaling up. And that's what we also hopefully see when we have 50 companies. Very likely not all 50 will survive, but some succeed and scale up. Yeah? And then we will definitely see a considerable reduction of cost. Yeah,
okay, thank you, good. And last but not least, I would end this round of questions with Wolfgang and talking about sustainability and circular economy. What is your view regarding the circular economy issues and life cycle assessment? For example, life cycle assessment is something probably we still do not look when we think about HTS. You mentioned that, but what is your view about the circular economy integrated in the system?
I'm not okay. On the life cycle, I don't know what was your question on that really, but I think at the moment we are rather at a stage where we have a lot of valuable candidates for products that we have a good chance that they could make that they could improve sustainability considerably, as Ziad has also shown in his presentation. And I think that's really the thing that we should put a focus on how to accelerate and how to realize and bring such systems to the market to benefit from that. That should really be our focus. And I agree that things like public-private partnerships would be a valuable tool to do that. I would add that what we see for example, also in the US, with milestone-driven projects. This should also be an add-on to have a clear roadmap to follow and clear measures for success of such projects.
Okay. Yes.
Yeah. I would like to bring to our attention, or to our mind at least, that superconductivity, and especially HTS, is one of the rare cases where efficiency in energy consumption or energy use and resources, efficiency in resources which are used, goes hand in hand.
Yeah.
So this means this is a strong step towards a sustainable or circular economy just because we are so resource efficient. That's great. And
Right. No,
if you know another example, fine. But this, I'm already excited by this real benefit of superconductivity.
That's one of the very important issues, because losses are also, sometimes we neglect them, but they are also very important. I think we have time for one or two questions from the audience. As a short summary, I would say that we are evolving from component to systems and to solutions, so I think this is the way to go. And also, we highlight that collaboration, either public, private, research, or companies, is of utmost importance to go forward and at the same time reduce costs by upscaling the systems. Nevertheless, if everyone is desired for the gala dinner or wants to ask one or two questions, we have time. Yes, please, if you can.
Yeah, it's almost good evening now, not good afternoon any longer, but thank you for the discussion up here. And sometimes I'm being accused for being very direct, so don't take it personal, but I do have a question to you, somehow representing the utility companies. I have attended here for the last 3 days. I have attended these conferences for the last many years. And I get very excited when I'm here, when I see what all the colleagues can do. Some of the best brains in the world are here together. And of course, we are living from the industry we are in. But there's something beyond that, because we also like to help. We also like to contribute to this transition that is going to happen. Doubling of electricity in Europe over the next 20 years. And the power lines we are having, the cables we are having, whatever it is, will not be enough. We have to build a super grid, so to speak. Parallel, on top, or whatever we want to call it. Now my question to you, and I don't know if you have attended over the last couple of days, would you at the next board meeting or the senior executive meeting come in with a new paradigm or some new ideas and share some of our passion about this? Or would you say, okay, job done, I attended for 2 hours and I'm out again?
Okay, great question. My job is research and development and innovation, so I'm not at, let's say, the decision-making level for grid investments or renewables investments. So I'm the challenger within the company. I was kind of putting myself somehow in the feet of these decision makers, but that's not me. My job is to challenge. So, I mean, I would return the question back to you, and perhaps challenging a bit the audience, which is the way we do innovation. We have several tools, R&D, venture capital, but one of the things we do is we have an internal development funnel, which is basically a huge amount of ideas in the beginning, and then we have some sort of shark tank that every 2 months meets and decides upon opportunities, whether they move or stop. And people go there, teams go there, and ask for money and time to develop their technologies. So we are eager to get, and we call them emerging business opportunities. We are eager to get one emerging business opportunity on the topic of superconductors within this funnel. So my question to the audience is, are there any companies, startups, that have a technology or a system that solves a use case in the energy sector, and you are willing to work with us and to, well, firstly to try to quantify what this use case is, and then to set out some sort of piloting initiative so that we can get confidence and go throughout this funnel. And the last stage is, of course, scaling it up to the business. So that's my contribution.
Thank you. We have one more question, time for one more question, but please don't answer João's question. Keep it for the dinner.
So there was a question about how the financing actually drives a lot of development. This example of Commonwealth future system was mentioned. So I was wondering, just one question, shouldn't be also investors on stage, if that's an important consideration? And the second follow-up question, so as a startup, what I see very often from large corporations is that they say, okay, I need to do technology which is 5 years from now. But those technologies in some cases don't exist. For example, aviation, sustainable fuel. All airlines want to decarbonize, but sustainable fuel is not available at the right price cost. So if you want to have the fuel available, you need to invest in startups, but this is going to take more than 5 years. So how do you bridge that gap? 5-year corporate development versus 10 to 15-year development of technologies like HTS.
Candidates for
I can take this last bit, but I mean, I don't want to.
Anyone?
Yeah. I think we need to understand our society needs and focus in developing this technology for a target. And this target should be either in our health or in our energy supply or as social being. So any program, you should have a consortia which based on expertise. Could be from the research, could be from the industry, but it should have focused with targeted objectives, with a proper funding to ensure it's delivering on the solution. If it's 5 years or 3 years, it should have an element where companies feel they can be part of it. It's very important that we understand where companies come from. They have a mission, and their mission is really to deliver services. And our focus should be to understand their mission and their services and come closer to them and understand how we can talk their language to deliver a solution. I can't see that by saying they will require a black box solution from us without understanding their requirements. So it can't be addressed offline. It has to be in partnership. That's where I strongly believe in that. And the alternative, we will get this incremental improvement slowly. If you give an example of electric car and what has been done in the last 10 years or 9 years, it was most of the major companies said we will not go for electric car. There's no need for it. Now, after it has demonstrated its performance, using regulation, so the subsidies for electric cars was so critical to allow electric cars on the roads, because it was linked to our society, the needs for the carbon emission, the clean economy, and so on. So that's what we have to understand our needs and link it to the solution and reach out to the decision maker, policy makers to deliver on that need. That's where we think we need a national initiative on superconductivity. The national initiative will provide the backbone for allowing the researchers, the experts, the small companies, and the end users to work together. Otherwise, we will be opportunists. That's how I see it. If there is something happening quickly, you can do it, but it will not address all our challenges.
Do you want to say something?
I wanted to make a comment, just to tell you what is the tool that we have. I mean, we do have a venture capital arm within our innovation area. It's a corporate venture capital fund. We have approximately 74 million euros invested so far, like in the last 10 years, more or less. But I mean, we invest in, I think, early stage or seed, I don't know exactly, to Series B kind of opportunities. And we invest, our investment tickets are 1 to 10 million euros. And there's one assumption, I mean, perhaps this could not be, if I was the only one to choose, perhaps I would be a bit more disruptive. But But I mean, the strategy that we've selected in our innovation area is to be what we call fast followers. So we don't go to very low TRLs, or we don't go to technologies that still need hundreds of millions of euros to be developed. So this is our niche. But I mean, there are for sure other venture capital funds that, or scale-up funds that I mean, my feeling is that there is money available to invest in such technologies. I mean, don't ask an utility which is somewhat risk-averse to be the driver for this. But I mean, we can contribute with, I guess, providing room for pilots to take place, etc. I think we can have our contribution to this development.
Thank you. So, I'm sorry, we have to finish. Please join me in a big applause for our panelists, and thank you very much for being here. So, the chairs told me that you should go to the gala dinner, which is...
Ja, ich muss jetzt erstmal auf dein Toilette
No,
ganz schnell.
thank you. Thank you. Sorry about the